Hi, a very good day to all. Today we are in the third session for Chapter 3 on the simulation of reactive processes. So we have gone through all the detailed lecture in session 1 and 2. So in this session, we are not going for any lecture, but we will be focusing on the exercise 3.5, just solving exercise 3.5. So let's go through the slides. So we have the problem here on the acidification reaction of ethanol and acetic acid, and the product is ethyl acetate and also water. Here, based on the chemical equation showing, is actually a reversible reaction. Okay? And the reaction condition here is 70 degrees C and atmospheric pressure. The kinetic parameters given here is the rate is in the unit of kilomole per meter cube per second. We have the pre-exponential factor and also activation energy for forward and reverse reaction. And it is mentioning that reaction are first order with respect to each of the reactants in the reaction. Meaning in total it is second order for the forward reaction and also the second order for the reverse reaction. Later on I will show you the details when we analyze the problem. The question is also stating that the reaction occur in liquid phase and the rate is in the basis of molarity, okay? Meaning the rate equation is written in terms of concentration. So the hints given here is you have to check that each reactor is considering liquid phase only as the valid phase. So bear this in mind when you want to do the valid phases in reactor, please choose only liquid. Okay, so this is a flow sheet given to you. You have to simulate the reaction stated in exercise 3.5 just now in different types of reactor with asteroid. Given the conversion of ethanol of 70%, we have R Gibbs, we have R plug with the dimension given, and also the RCSTR with the volume given to you. Okay? And the property method recommended here is NRTL to describe the property in liquid phase and HOC to describe the properties in vapor phase. So the feed condition is also given. The feed condition is just like the reaction condition, 70 degrees C and 1 atm. The water, ethanol and also acetic acid compositions are given accordingly. Water present in the raw material because of, I think this is impurity in one of these raw material, either ethanol or in acetic acid. So let's analyze the problem. So the components involved in this case, of course, we have to include the reactants as well as the product. In the case of you are having other impurities in your raw material or in your product, you have to include all in the list of components. Then, in terms of the model involved, other than the reactor model, R stoid, R Gibbs, R plug, and also RCSCR, you need the duplicator here to duplicate the stream. That means to photocopy the stream to 4 branches, because you would like to simulate the same reaction in 4 different types of reactor. Okay? Duplicator is under the manipulator block. So later on I will show you. Okay? Kinetic, we have 2 reactions, one forward and the other one is reverse reaction. Forward reaction is acidification reaction producing ethyl acetate and water. This is a rate equation, second order in total, first order in the ethanol and first order in the acetic acid, and molarity base, meaning concentration base, and with the pre-exponential factor given as below. Okay? Similarly to the reverse reaction, we have the hydrolysis of ethyl acetate. So in this case, ethanol and acetic acid will be the product. Again, the Ray equation is stated in terms of first order in the ethyl acetate and first order in the water with the pre-exponential factor and also activation energy. So as usual, we have to create a blank simulation and then list down all the components, select the property method, and generate the properties for all the components before we can shift it to the simulation environment. So in this case, you have to first construct the flow sheet. So as I mentioned earlier, you need a duplicator to duplicate the number of streams. So in this case, I'm going to show you two examples. One is the R Gibbs, the other one is the R plug. Okay, so we will choose this duplicator under the manipulator block. Okay, so once you have this, you can have one inlet. This is your feed stream, and then you can have multiple outlet. Meaning, if you would like to have the same stream for twice, then you branch it into two. If you would like to have the same stream for 4 branches, then you have to branch it out to 4 streams. Okay, so just like this, I branch it out into 2 because I would like to show you R Gibbs and also R PFR. So next, you have to complete the flow sheet by putting in the block for the reactor. We have R101 here for R Gibbs and R102 for R plug. So let's complete the block spec. Here I'm going to show you the block spec for R Gibbs. Block spec for R plug is actually quite straightforward. I will leave it to you. So what you need to do is, in terms of calculation option, you just calculate the phase equilibrium and also chemical equilibrium. On these two equilibrium basis, we do the calculation. Put in the reaction condition, 1 atm and 70 degrees C. So remember, the reaction happen or the valid phases is only liquid phase. You have to uncheck this, include vapor phase. I think by default it is checked, but you have to uncheck this before you proceed. Okay, once you have included the block specification, then you have to include the reaction details. Remember, you have to click new, create the new reaction set. Then the default name for the new reaction set will be R1. Remember to choose general type. Okay, don't choose any other type like power law, Langmuir-Hinshelwood, but choose general type before you proceed further. So once this is done, then if you don't know which tab to go, then you just click next. You'll be guided to the reaction area for you to include the details of R1, the reaction set. So we have 2 reactions, one forward, the other one reverse. So for forward, you just need to click new and put the name as forward. Forward, of course, ethanol and acetic acid will be the reactant, and the ethyl acetate and water will be the product. So just put it accordingly. And now this reaction class, you have to put it as power law. Okay, once it is done for forward reaction, then close it, and you can create another one for reverse reaction. Just put in the details accordingly, but this time ethyl acetate and water are your reactant, while ethanol and acetic acid will be your product. Okay, once this is done, close it. Then you'll be guided to the kinetic tab. Under kinetic tab, you will have a drop down list here. You will have, if you have included 2 reactions in the configuration tab just now, then you'll be having 2 reactions in the drop down list. So you select the first one and put in the kinetic data accordingly. Liquid phase, the basis is molarity, so the rate basis is volume basis with the unit of kilomole per meter cube per second as stated in the question. Then you put in the pre-exponential factor and activation energy. Remember, the unit for your activation energy must be correct. If you have chosen the wrong one, then all the simulation result will be wrong. So next would be your driving force to put in the order of reaction. So the order of reaction would be first order in ethyl acetate. Driving force for the first reaction you have to put in on your own. First order in the ethanol and first order in acetic acid. If you choose the second reaction in the drop down list, and then you put in the kinetic details, and this is an area for you to put in the driving force, the order of reaction. So everything is the same with the forward reaction, but in this case the order of reaction is first order in the ethyl acetate and first order in the water. Right. So once all the details are included, then just run the simulation and check the result. Here you are asked to check the molar flow rate and also the mass fraction of the product, which is ethyl acetate. That is your main product. So let's check under the result summary, the stream tab. So you have ethyl acetate here. My product is actually S4 is the product stream for R Gibbs and S5 is the product stream for R plug. Okay, just check accordingly, and this is the mass fraction for ethyl acetate in the product stream, okay, 0.55 and also 0.54 for RPFR. 0.55 is for R Gibbs. So you can also check the heat duty under the model tabs, okay, under the section of result summary. So we have the heat duty for R Gibbs. You can also check the heat duty for R plug accordingly. Okay. Other than this section, you can also check the heat duty in the block area. So you can go to the block area in the navigation pane and check the results accordingly. It is also available in that section. So I have shown you how to do it in R Gibbs and R plug. So R stoid and R CST, I will leave it to you. Okay. So once you have done, you can compare your result with the answer given in Exponent Plus. But just to let you know, the heat duty here, I think they have been given in error because we have done it for so many times, and we are able to get the ethyl acetate molar flow rate and also the mass fraction, but it's just the heat duty is different from our answer. It's okay as long as you can get the mass fraction and also the molar flow rate of the ethyl acetate. It shouldn't be a problem. Okay, our heat duty is the correct one then. So this will be your homework. Please complete R stoid and also RCSCR. And with this, I think this is all for session 3 for chapter 3 on the reactive processes. I hope you can get some new information here. At least you know how to simulate a kinetic-based model, more than one reaction. Here we are having one forward reaction and one reverse reaction. You may have more when you have more side reaction in your project or in your plant design later on, right? So with this, I thank for your attention and enjoy doing your homework. Thank you very much.